So next up we have Matt Amy from Simon Fraser University, who will be talking about automatic generation of classical invariants of quantum programs.
All right, thanks for the introduction. It's kind of unfortunate that I'm going right after Craig's talk because one of the applications was going to be for T-count optimization, which I guess is now irrelevant. But yeah, hopefully there will still be some interesting stuff there for you guys. Okay, so this talk is based on some work that I did with one of my students, Joseph Lunderville, and the paper was published in POPL, which is a programming languages venue, right? So thank you to the program committee for selecting kind of, I guess, what might be a slightly different talk for QIP here, but you know, hopefully we can all learn something fun. Okay. So what is this talk about? What is this work about? This work is really about this classical invariant problem of quantum programs. So what I mean by that is specifically given a QRAM program, and here I mean QRAM in the sense of many-nil, like quantum data classical control, not QRAM like you all think of it now. So quantum data classical control program, compute a logical or algebraic property that characterizes the classical transitions of the program. So specifically bit strings x and x prime, such that when we run the program on initial bit string x, we have a non-zero probability of measuring x prime. Right? Okay. So for those of you who aren't aware of what I'm talking about when I talk about invariants, I'm really just talking about a logical property of a program that's true. And we've all seen examples of invariants in this room, right? When we learn Grover's search algorithm, this is pseudocode for Grover's search, right? When we learn Grover's search algorithm, we learn it implicitly by learning the loop invariant, right? And the loop invariant of Grover's search algorithm is the fact that our state on every entry to that loop lives in this two-dimensional Hilbert space, right, spanned by these two particular states. So that's an example of a loop invariant, right, a logical property that's true every time we enter the loop. And a loop invariant in this form is an example of a state invariant. So state invariants state logical properties of the set of states that may enter a particular location in a program, right? But we can also consider other types of invariants, like relational invariants, which is what we're interested in with this work. Relational invariants are logical properties that relate the output of a program to the input, right? Or the state at one particular program location to the state at another particular program location. In particular, right, if we have a loop, we can have a relational invariant of a loop, which would be a property, right, of the output that's satisfied when we have a certain property of the input, right? If we take the fixed point of this, we actually get a state invariant of the loop, right? Okay. But why specifically classical invariants, right? We're talking about quantum programs. We're at a quantum computing conference. Why do we care about classical invariants? Well, kind of two reasons, right? One is that they're actually computationally tractable in polynomial time in certain cases, right? And in other cases, still a little bit more efficient to do than full kind of quantum invariants, right? But then the other reason is that they're useful. They're useful for doing things in verification and circuit optimization. So what are some things that we can prove using classical invariants, right? We can prove, for example, that an ancilla is returned to the zero state, right? Or maybe that a gate has no effect on the state, so it can be removed in a circuit optimization. And this particular work, we were looking at a certain property, looking at proving a certain property, right, which is that a diagonal gate can quasi-commute through a program. And by quasi-commute, I mean commute through a program, but potentially to some other diagonal gate, right? It might be changed by the program, but it can still commute through, in a sense. And the reason for this is it allows us to extend quantum circuit optimization to quantum programs. And specifically, this is the phase folding optimization that some of you may be familiar with. So the idea behind the phase folding optimization is to reduce the number of T gates, or generally higher order rotations, right, in a quantum circuit, maybe over Clifford plus T, right, by finding instances of T gates that can cancel or otherwise merge to an S gate, right? And one of the ways that we can do this is by mapping, say, a Clifford plus T circuit to a string of Pauli exponentials, right? Rotations of angle pi over 4, right, around a Pauli. Because each one of these corresponds to a T gate conjugated by Cliffords. So once we've mapped a Clifford plus T circuit to a string of Pauli exponentials like this, right? We have k T gates, and we want to reduce the number of T gates. So what we can do is we can use those Pauli commutation relations, right, to find pairs of Pauli rotations that are effectively adjacent, right? And then cancel them or merge them if they're the same Pauli, right? And there are lots of other ways of doing this optimization, lots of other formalisms, things like phase polynomials or the ZX calculus. You can do the same optimization, all kinds of formalisms. But the idea is, right, or the key part is that we have a formalism that represents quantum circuits. And that's what allows us to actually do this optimization, taking a circuit and representing some other formalism that represents circuits, but kind of mods out by the Clifford effects. Problem, of course, is when we get to the real world, we don't just have a single quantum circuit, right? We have a program that maybe has some classical control, is interleaving quantum instructions with classical control. This is happening more and more now, right? Quantum toolchains are starting to move to this hybrid model where we actually have tightly interleaved classical control inside quantum computations. Because a lot of the stuff that we actually want to do now with quantum programs, or in the future, right, because we're not running these things, will actually have this kind of interleaved classical and quantum computation. So this is an example of a repeat until success circuit, right? And when this loop exits, when it gets a certain measurement result, right, it'll exit having applied a particular diagonal gate on the target. Now, because we know that a diagonal gate will have applied, right, we can actually commute this T gate through from the left-hand side, right, to the right-hand side and cancel it out. The thing is that existing circuit optimization methods can't do this, right, because we don't have a circuit. We have a program. So what can we do? Well, the fact that it ends up being diagonal on the target means that it satisfies this classical invariant where in the computational basis, the state on the target is not changed, right? So that allows us to actually do this commutation, at least in our formalism, allows us to do the commutation of the T gate through that while loop, right? At which point it can cancel out with the T dagger. Okay. So that was kind of a simple example, right? We can imagine how we might do that just because the body of the while loop was actually diagonal on that target qubit, right? So you can imagine how maybe a quantum compiler could see this optimization. But what about this program, right? Where now we have this while loop that's going to execute an unknown number of times. It's a non-deterministic while loop. That's what I mean by the star here. Well, one of the things that we can notice in this particular case, right, is we don't know the state at the end of the while loop, but we do know one thing, right, which is that the sum of the 2 bits is not changed by the while loop, right? We just swap the 2 bits some number of times, right? So their sum, at least in the computational basis, is not changed, or that is an invariant of the loop. After we exit the loop, x prime plus y prime is going to be equal to the input state x plus y, right? And now what that allows us to do is to actually commute this diagonal gate on the left-hand side here, right? This is a diagonal gate, and what it's doing is applying a pi over 4 rotation conditional on the sum of the 2 bits in the computational basis, right? So it's conditional on the sum of the 2 bits in the computational basis. It can commute right through that gate or right through that loop because that loop leaves their sum invariant, at which point it can cancel out with the diagonal gate on the right-hand side, right? Okay. So how can we formalize and compute these invariants and do this kind of optimization, right? It turns out that coming up with the right formalism was kind of the hardest part of this work. It's going to sound silly when I show it in the next slide, right? But that was, and then once we had the right formalism, kind of everything just fell out in a pretty straightforward manner. Okay, so the way we formalized this, right, was by defining a notion of the classical semantics of a quantum circuit, right, or a quantum program. In particular, we say that the classical semantics is the non-zero transitions, right, that, say, a unitary can take between classical states. So we're really viewing, say, a unitary or a circuit, right, as a classical non-deterministic transition system, right? So we define the classical semantics, right, of course, as the set of pairs x and x primes, such that if we apply the circuit U on the initial state x, right, we have a non-zero probability of measuring x prime in the output. Now, with this definition, it extends in a very natural manner to quantum programs because we're really viewing it as a classical program in the first place. So when we add classical control to that, all we're doing is we're analyzing a classical program, right? So in our program model, we have quantum statements, right, a language of quantum statements that includes things like measurement and unitary applications, right? And then we have classical control built on top of that takes the form of regular expressions, right? This is a common thing that we do in program analysis. We view non-deterministic programs as basically regular expressions. Okay, so then we say that the classical semantics of such a program is really just the union of the classical semantics of every individual possible run, right? Okay, so now that we have our definition, right, we can start thinking about how we might compute the classical semantics, right? And there's a problem, and that problem is obviously that we can't compute the classical semantics. We have this infinite union over an infinite number of runs, right? So what we have to do, and what we do in program analysis most of the time, is we come up with some sort of approximation. And by approximation in this case, I mean we're going to find some relation that contains all of the classical transitions of the program, right? And maybe some extra ones, right? But as long as we have all of the classical transitions of that program, we know that any property that's satisfied by R is also going to be satisfied by the program itself, right? And it's easy. It's easy to create an approximation. One simple approximation is by just taking the interpretation of regular expressions on relations. So we know that relations, we can compose them in sequence using sequential composition. We can compose them in parallel or choice, right, by taking their union. And we can also take their transitive closure that corresponds to the iteration of a relation. Okay. So this model is now computable, but it's exponential time to compute this approximation of the classical semantics. And not only that, but there's this other issue, right, where it's not really logical. We end up with just some sort of set of states. We don't know anything about the set of states. We don't have anything useful that we can do with this set of states, right? So we need to tease out some sort of structure so that we can actually learn about the program. And if we want to tease out some sort of structure, right, we can go back to our gate basis, like, for example, in Clifford plus T, right? And if we look at the standard generating set for Clifford plus T, right, we see that they all implement affine classical transformations, right, in the sense that the X gate, for example, applies an affine transformation to a classical state X. It just maps it to 1 plus X, right? So that's kind of the view of these gates as affine transformations on the classical basis state, right? But if we instead view them as subsets of the input state times the output state, right, that becomes an affine subspace, right? That's equivalent to just saying an affine subspace rather than an affine transformation. In particular, the classical semantics of all of these gates are exactly affine subspaces of the input and the output space. And here I'm using angled brackets to denote the smallest affine subspace, satisfying that particular relation. So in this case, being that the state of the qubit is unchanged in the computational basis. Okay. So we have kind of our idea of our domain for where our program analysis is going to take place. Now what we need to do is build up the analysis in some sort of way. And the standard way that we do this is compositionally, right? So we want to define a notion of sequential composition branching or alternation, right? And then also iteration on our domain, which is affine subspaces. And it turns out that we can do this relatively easily, right? Because the lattice of affine subspaces of a vector space forms a Kleene algebra. Kleene algebra is just an algebraic axiomatization of regular expressions, right? But basically what it means, if we have a Kleene algebra, then we can coherently interpret regular expressions in our algebra. And we do have a Kleene algebra here. In particular, sorry, I just had a notification. The additive unit is just the empty subspace, right? The multiplicative unit is the identity transformation, right? If we want to do sequential composition, it's just relational composition, which corresponds to projection and intersection subspaces. The union is the least upper bound in this lattice, which is the smallest containing affine subspace, right? And then if we want to do iteration, right, all we need to do is construct this ascending chain, right? And our lattice has finite height, right? Because we can have at most a subspace of dimension 2n, right? So if we keep going up in this lattice, right, if we keep finding bigger and bigger subspaces, right, eventually we'll get to the top. And specifically, we'll get to the top in at most 2n, 2 times n iterations, right? Because if we have this ascending chain, each one is going to increase the dimension until it stabilizes. Okay. So the result of all of this is that we can, in polynomial time, take a QRAM program P and compute an affine subspace that soundly approximates the classical semantics of that program, right? And if we apply it to our previous example, right, this while loop with the swap inside, we find that the loop invariant that we actually compute is exactly the smallest affine subspace that satisfies this relation that I showed on the previous slide. Mostly that the sum of the 2 bits is unchanged. And now if we want to actually do that optimization where we cancel out these 2 diagonal gates, what we can do is we can take the condition of the diagonal gates, right? They're both conditional on the sum of the 2 bits. So we take the condition on the diagonal gates and reduce them modulo that subspace. And we find out that they're applied in exactly the same instances, so we can just merge them into a single diagonal gate. Okay, so what if we need more precision, right? So if we take that previous program and we replace the CNOT gates with Toffoli gates, we can still do the same optimization because that loop also preserves the product of the 2 bits, right? But the problem, obviously, is that we have an affine loop invariant, right? So we can only prove linear properties or affine properties. We can't prove nonlinear properties like x prime times y prime is equal to x times y, right? So to be able to get this optimization, now we need to expand our domain to include nonlinear classical reasoning. And turns out that that's easy again, right? Because just like we can generalize linear algebra to nonlinear algebra using Grosvenor bases and polynomial ideals, we can do that in this case too. So we replace affine subspaces with affine varieties, we replace affine relations with polynomial ideals, and then we can just use Grosvenor bases to implement the Kleene algebra operators that we need to actually interpret a quantum program. Okay, simple stuff. Rather than going into the technical details, just a quick note or a couple of quick notes, right? So this is, in fact, precise. This analysis is precise for the compositional model that I gave a few slides prior, this R of P. Right, but it has this additional structure where now we not only have the set of transitions, but we also have basically a set of polynomials, set of polynomial relations that are satisfied by these classical transitions. So we have more structure. And we can ask, do we have all the polynomial relations satisfied by the classical semantics? In this case, we do. We get all polynomial relations implied by the variety corresponding to that compositional model, and that's due to kind of an esoteric form of Hilbert's strong Nullstellensatz for finite fields, where the radical of an ideal is just the ideal plus the field equations. Okay, so the catch. There has to be a catch, right? And the catch is that if we view things strictly classically, if we view quantum programs as just classical transition systems, right, then sequential composition is not precise. And not only is it not precise, but it's really, really not precise. Like this kills the technique without doing a little bit something extra. So in particular, if we view the Hadamard gate as classical non-deterministic transition, right, we have every possible transition from one classical bit to another classical bit. So now if we compose those, right, as classical processes, we have every possible transition, again, from one classical bit to another classical bit. But we know if we multiply two Hadamard gates together, we get the identity. So we only have the classical transitions between 0 and 0 and 1 and 1. Okay, so how do we reconcile that? Well, our solution was to use the sum over paths to generate precise transition relations for the sequential fragment of these QRAM programs. So sum over paths is an expression of, say, unitary operator U, and its action on a computational basis state, ascending that computational basis state along a whole bunch of other paths indexed by binary variables, right, to an output state that's given as a polynomial function of the input and path, right, along with some sort of amplitude. So the way this works roughly is that we can compute a syntactic encoding, which I use these banana brackets to denote, right, of the sum over paths for a circuit in polynomial time, right? And now once we have this syntactic encoding, what we can do is we can extract a valid or sound polynomial transition ideal from that directly. It just gives us the polynomial transition ideal, right? And this at face value doesn't actually increase the precision of the analysis. But now what happens, we have this syntactic encoding of the path integral, right? So we can use that to actually analyze interference and eliminate some of these spurious paths. In particular, right, if we have a path integral of this form, then due to interference, we actually see that we can make our transition ideal a little bit stronger by taking the meat of our transition ideal given by the sum over paths and this additional polynomial equation that p is equal to 0. Okay, so is this useful, right? Well, we did implement this. We implemented this on a subset of OpenChasm3 that includes loops and if statements, just to test out the ability to generate these invariants and do optimizations, right? We found that we can actually get some interesting invariants and interesting optimizations for simple programs, right? But the main point here is that this technique allows deep integration of circuit optimizations in compilers for these hybrid tool chains, these hybrid workflows. And the other thing that came out of this that was actually kind of really fun was we found moving to this invariant-based approach actually allowed us to do strictly better phase folding type optimization. So it strictly outperforms existing phase folding optimizers. In particular, it recovered this one nice optimization of dirty ancilla multiply control Toffoli due to Dmitry Maslov. So in this standard kind of Barenko style dirty ancilla multiply control Toffoli gate, we can actually eliminate a couple of T gates from these Toffoli gates that are noted here, right? If we know that the dirty ancilla A is returned to its initial state at the end of the circuit, right? So that's what Dmitry Maslov did. The problem is, in order to prove that, we need nonlinear classical reasoning, right? So no existing automated approaches have been able to get this optimization. But we did manage to get it with this invariant-based approach. So that was really cool. And then last thing I'm going to say, I was reading a paper recently by chance by Craig Gidney and Tanish Qatar, Rise of Conditionally Clean Ancilla for Optimizing Quantum Circuits. And I happen to notice that this one particular circuit construction that they have has the exact same structure where it's got these cascades of Toffolis, right, at the outer edges of the computation that are using dirty ancillas, right? So I was thinking when I saw this that existing phase folding optimizers will get the optimizations for the inner one, okay, but not the outer ones, and that's exactly what happened, right? So when I ran existing optimizers, right, got the T count down to 11, K minus 2 plus 7, right? With the invariant-based approach, we get down to 8, K minus 2 plus 7. Which was really cool because this actually halves the T count of the best previous construction. Okay. Yeah. But that's all I really wanted to say outside of the fact that we're looking for other applications of this kind of work. Obviously, there's applications to verification, but if you have other thoughts, I'm happy to hear them. Okay.
Okay, thank you. Are there any questions from the floor?
You flashed this table that had a line with Shor's algorithm on it. Do you want to, can you comment on that a little bit?
Did I? This one? Yeah, so these were just some of our experiments on applying our procedure to quantum programs that actually have loops. And so one of those examples was an instance of Grover's algorithm. It wasn't really the most interesting one because most of Grover's algorithm in this case happens inside of that loop, right? The optimizations that we got were really the preconditions of the loop. So when we compute this invariant, right, that effectively gives us a precondition for the loop, or an invariant that's satisfied every time we enter the loop, right? By seeing that this invariant is satisfied, in particular it was that some of the ancillas are in the 0 state, it actually allows us to optimize away some of the T-gates inside that main loop of Grover's algorithm, right? Yeah, so that was what was happening in that one. And the rest of these are all kind of just examples trying to look for interesting invariants of loops.
So it's finding in the goal state that it has some zeros set already, and so you can remove all of the controls on that. Is that how I should think of that?
Yeah, basically. So if the ancillas are initially 0, right, the first time you enter that loop, you can do those optimizations. That's fine. That's doable using existing techniques. The problem is if you want to keep all of that inside the loop, right, you need to prove that those ancillas are 0 every time you enter the loop, right? So existing optimizers can't do that. Until you look at proving these invariants, which are that every time you enter the loop, the ancillas are 0.
Thank you.
Okay, are no more?
Is this on?
Yeah.
It is? Okay.
So you're using the Toffoli decomposition that uses 7 T-gates, right?
Yeah.
Have you considered trying to apply this technique when you're applying Toffoli's by gate teleportation from a Toffoli state, where basically the equivalent would be when you do that teleportation, you need a CZ correction if the targets disagree, and when you later perform the Toffoli again or uncompute it, the CZ correction will appear again and they can merge.
Yeah. Yeah, so that was kind of those kinds of programs were exactly the ones that motivated this work, because we were looking at ways that we can extend existing optimizations to these programs that have, say, classical control. In that case, it's not looping classical control, but if you want to extend circuit optimizations to programs that have classical control in